Welcome back to another video of linear algebra. Yay. I'm not very excited for this one. Primarily because this is more on the heavy side of conceptuality. Additionally, this is the only or one of the topics in linear algebra that a lot of people start getting lost, confused, and then just be behind of everything else. I was one of those people. But the good news is we're done with matrices, or most of it. I believe it's all of it. And so now we're going to focus on a new topic, which is vector spaces and subspaces. Like I mentioned before, this is the topic where people start getting lost. But for me, in this series, I'm going to probably focus more on subspaces and more on how to find them than just focusing on the conceptual side. I highly recommend looking for other resources for these types of videos. Khan Academy is like highly recommended, but if your teacher can help you out, by means use it. So yeah, let's get started. So we're first going to talk about a vector space, and we've been talking and using vectors a lot, even before linear algebra, for example, in physics, mechanics more specifically. You do use vectors, but I don't think they've told you what a vector really is. A vector space is probably more confusing since a vector space and a vector are not the same. But we're going to get started. So a vector space is a set V. It could be any letter, but usually denoted as capital V, whose elements are called vectors. You've heard that before. And that can be added together and multiplied by a scalar. In other words, a vector space is just a set that follows these conditions, which can be added together or multiplied by a scalar. That means that all vector spaces are sets, but all sets are not necessarily vector spaces. They have to satisfy certain conditions, which would be 10 axioms that they follow. And an axiom is just basically a proposition that is that just sets the foundation of everything else. You've probably dealt with them before, but you just didn't know that there were axioms. A common example they probably learned in algebra would be for the axioms of real numbers, particularly the identity axiom, in which any number multiplied by 1 is that number itself. So that's the identity in multiplication, and then for addition, it will be any number plus 0 is equal to that same number. But yeah, vector spaces must follow 10 axioms. 5 of them are from addition, and then the other 5 are from scalar multiplication, since that's what you can do, add them together or multiply by a scalar. These simple things that you can do, adding and multiplying them by a scalar, are very powerful and very useful when it comes to dealing with vector spaces. And so if a set fails to follow any of these axioms, then it is not a vector space. So the vector spaces are restricted under these 10 axioms. If you just fail to follow at least just one, then it's not a vector space. So I think this video will mostly cover the 10 axioms of the vector spaces. And so let's just get right into it. So before we talk about the 10 of them, let's just set the proper definitions and what we're going to be working with. So we're going to let V, U, and W be in the set V, and scalars A and B be in the set of real numbers. What that basically means is that V, U, and W are vectors, and A and B are real numbers. So the first ones, or I guess the first 5, is going to be under addition. The first axiom would be that it's closed under addition. So that means any two vectors, in this case U and V, when you add them together, its sum would also be in the set V, or capital V. The other one is the commutative, which the order doesn't matter when you add them. So the vector v plus u is the same as u plus v. Or the third one would be the associative property, in which it doesn't matter which two you add first, they'll result in the same sum. So in this case, we have vectors v and u added first and then added to w. And this is the same as adding vector u, v, and w. No, my bad. It's the same as adding vectors u and w first and then acting vector v. The fourth one is the zero element, which basically implies that there exists a zero vector in the set capital V, such that any vector plus zero is that vector itself. So that means zero has to be in the set. And then lastly, it's the inverse. So that means there exists some vector, we're just going to call it negative v, in the set of capital V, such that when you add vector v plus negative v, that'll just give you 0. That's pretty much it for the addition axioms. We're now going to go over the last 5, which are from scalar multiplication. Again, we're still going to be working with vectors v, u, and w, and the scalars a and b. And so for the scalar multiplication one, there's the easiest one, which is closed under scalar multiplication. So that means any scalar multiplied by a vector in the set would also be in the set. The next axiom would be the distributive property, and there are 2 of them. So the first one is the sum of 2 scalars multiplied by a vector is the same as the sum of the 2 different scalars multiplied by the same vector. And then the other one would be the sum of 2 vectors multiplied by a scalar is the same as a scalar multiplied by a vector plus the same scalar multiplied by a different vector. That b is supposed to be an a. My bad, let me fix that real quick. There we go. Alright, so the last 2 would be the associative property. So it doesn't matter if you multiply 2 scalars first and then the vector, or a vector and a scalar and another scalar, they should give you the same result. And the last one would be the identity vector, where any vector multiplied by 1 is the same vector. And yeah, that's all the 10 axioms for the vector spaces. And now we're going to talk about subspaces. So subspaces are another set, but it is in the vector space. So a subspace is just a smaller vector space that's contained under a much larger vector space. Because S is a vector space, to really check if it is a subspace, then we just need to check 3 things instead of the 10 axioms. The first one would be the closed under addition, and then closed under scalar multiplication, and then containing the 0 vector. And that's pretty much it for subspaces. Again, we're going to do some examples, particularly focusing on subspaces. Vector spaces, it's just pretty much checking all the 10 axioms. But with subspaces, there's different ways they could ask you with subspaces. One of them is finding them. The other one is if it's in a subspace, or if the subspace is in, or if the subspace exists. But yeah, I'll see you guys in the blackboard. All right then.